Hello guys, how are you doing? So far, not so many of us have joined. Apparently it's because outside is quite good weather today. People don't want to go to lectures.
Professor,
Yeah.
If the work is negative, should I write minus sign as an answer, yeah, before digits?
Yeah, if work is negative, you should put minus.
Okay.
Okay, I don't know why today are not many people, but whatever. Anyway, we record all our class discussions. So apparently they will be able to see the discussion, to follow our discussion on Moodle, who hasn't have yet had a chance to join us. Today we will have also quite a bit of new material. So let us try to do our best and discuss most of the topics I would like to highlight in our today's discussion. Yeah, hello everyone who just joined. Nice to see you guys. And let's start working. Oops. No. Maybe some technical issues, but hopefully we will solve this. What's going on? Used to be without problems, but finally. Okay, so during our last discussion, we started a new topic, which is rotation of rigid body. And we clarified that we can describe this rotation, its kinematic features, where three different parameters. So one is theta, its angle, how much we change the angle defines the angle of rotation. Then we have omega, which is angular velocity. And this is vector quantity. It shows, first of all, how fast, its magnitude shows how fast the rigid body spins, and its direction, which is always along the axis of rotation, but its orientation defines also in which direction this body rotates. It's either clockwise or counterclockwise. So the direction of the omega vector will change for these two cases. And also we have, let's call it alpha, also vector value, it's angular acceleration. So it shows how fast we change the angular velocity vector, and its direction is either in the same direction as angular velocity if angular velocity increases, or it will be in the opposite direction to angular velocity vector if angular velocity decreases. So it slows down the rotation. So of course, if we compare these parameters with translational motion, we can find some analogies with x, linear velocity, and acceleration. Okay, now since we considered already kinematic features of rotation of rigid bodies, we should proceed further and consider some kinetic energy of rigid body rotation. So when we have this case of rigid body rotation, we do not have movement of the body in space, so it stays in the same position. However, parts of the small parts of the body from which it consists of, they move in the space. In particularly, they follow some circular trajectory, and that's why each small part of the rigid body will possess some kinetic energy. Let us try to figure out kinetic energy of these parts, and later we will apply like integrated approach to calculate kinetic energy and features related to this for extended rigid bodies when we have some continuous distribution of mass in different shape. Okay, let's have a drawing for now. We have some rigid body of any shape. This axis of rotation, let's call it Z axis. So here it interacts with this, intercepts with the rigid body. Then we can pick up any small part of this rigid body with mass mi, and it will be at a distance ri from the axis of rotation. And since it moves along circular trajectory, it will also possess some linear velocity vi. Okay, let us write the expression for kinetic energy of this part of the rigid body. So kinetic energy of this small part of the body I will be equal to mi times vi squared divided by 2. It's standard definition of kinetic energy, which we already are familiar with. So then the kinetic energy of rotation of this rigid body would be the sum of kinetic energies of each of its parts. So that's why kinetic energy of rotation will be equal sum over all I, Ki. And this is equal sum over all I MIVI square divided by 2. So we need now take into account what we discussed quite early in our course and also last time, the relationship between linear velocity and angular velocity. So V is equal to R omega. Now we substitute it here, and what do we get? It will be, we can take 1/2 outside the sum, will be 1/2 sum of all over the I, small parts of the body. It will be MI RI square omega square. So omega is constant for all parts of the rigid body. It's the parameter which describes all parts of the rigid body, so it doesn't change from part to part. And this will be equal to, so we can write, maybe let's write separately, that kinetic energy of rotation is equal 1/2 sum of all over all parts of the body, products of MI RI square. Let's take it in parentheses, times omega squared. So this parameter, which is in the parentheses, is called moment of inertia and is defined as I, capital I. So moment of inertia is equal to the sum of all, for all parts of the rigid body, MI times RI square. And we can, first of all, we define the units for this moment of inertia. Its units are kilogram times meter square. And now we can write final equation for kinetic energy of rotation of rigid body. Will be 1/2 I, capital I, and times omega squared. So if we compare this with the kinetic energy for translational motion, which is mv squared divided by 2, we see a clear correlation and analogs with these two expressions. So for the rotational moment, linear velocity role plays angular velocity, and for mass, it plays moment of inertia plays a role of mass in translational in rotational moment. So that we keep in mind, and also probably would be good to highlight that if we have a combination of translational and rotational movements, plus this body is rigid body is located in some gravitational field, then the total energy of this mechanical energy of this body could be defined as mgh, which potential energy, plus mv squared divided by 2, which is kinetic energy of translational motion, plus capital I omega squared divided by 2, which is another factor of kinetic energy of a rotational moment. So that please keep in mind. So now the important part is to understand very clearly how we are going to calculate the rotation, this moment of inertia. So let us consider first one simple example with like point masses, and then we will proceed further for distributed bodies. Okay, so let us consider such system of point masses. Will be some kind of form of cross. Then we have two masses, capital M, and two masses, oh sorry, just M. So we have here distance A and another A, so they're symmetric, and here B and B. So we neglect with the size of these bodies with masses M and capital M in comparison to these distances. So they are kind of point masses. And let us assume that this system rotates about axis Y. So we're interested in moment of inertia of this system of masses, four masses, about axis Y. So for this purpose, we need to apply our previously derived equation. It will be sum over all masses, mi times ri squared. What is now we need to consider? We have this capital M masses at distance a from the rotation, from the axis of rotation. That's why we have one product, M times a squared, plus another product, M times a squared. So we don't have any contribution from masses like M along axis Y, because we neglect with their dimension, and that's why distance from the axis of rotation is equal to 0. So if we have something multiplied by 0, we get 0 value. So we masses like M along axis Y will not contribute to the moment of inertia for rotation about axis Y. And this is equal to 2 M capital M A squared. And if we calculate now kinetic energy of this rotation about axis Y with some angular velocity omega, it will be the following. Kinetic energy of rotation along about axis Y will be 1/2 IY omega squared. And this is equal to 2m a squared omega squared divided by 2. We cancel out this 2 and eventually get capital M a squared omega squared. So if we consider rotation around axis, about axis x. In this case, capital M masses will not contribute. And following this procedure for calculation moment of inertia, we can write that moment of inertia about axis x will be equal to 2mb squared, because its masses m are shifted from the axis of rotation by distance b. Okay, so now let us consider the case when all masses contribute to the moment of inertia. And that is the case when we start to spin, to rotate this system of masses about axis which goes through the center of this cross, perpendicularly to the plane of the image, which let's call it axis O, and which means that we rotate this system of masses in the XY plane. So in this case, we need to consider contribution of all masses. And moment of inertia in XY plane will be equal, again, so we have a question. What is this formula and what is the... Oh, okay. So we are talking about moment of inertia of rigid body which rotates about fixed axis. And this J is actually not J, it's I. I is, we defined it previously as moment of inertia by considering the kinetic energy of rotational motion. So here is kinetic energy of a small part of rigid body which moves together like as a part of rigid body. Then we substitute value for linear velocity as a product of radius, the distance to this from the axis of rotation to this small part of rigid body, as a product of this distance and angular velocity. Then we consider the sum of all parts of rigid body for the product for all parts of mass and its distance from the axis of rotation squared. And this sum we define as moment of inertia of the body. And that's why now we are trying to learn how to calculate this moment of inertia for different bodies. And this is one of the examples how to do this. And K is kinetic, capital K is kinetic energy of rotation. Okay, so now you are welcome to follow us. And again, we have this, we want to calculate now the moment of inertia when the system of bodies rotates now in the plane of X and Y about axis O, which goes perpendicularly to the XY plane and goes through the center of this cross. And for that, we apply this equation, which we derived previously for moment of inertia, which is mi ri squared, sum of this product for all masses which are involved. Now, in this case, all four masses are involved. And we can sum this up. So it will be m a square plus capital M a square now plus mb squared plus mb squared. So we eventually have 2ma squared plus 2mb squared. And the kinetic energy for such rotation in the plane x, y for this given system of masses will be 1 over 2 I x y omega square, and this will be ma square plus mb square times omega square. So you see, depends on the location of the axis of rotation, we will get different values for the moment of inertia. That is the main feature of this parameter, that it can be for the same system of bodies or the same body different if it rotates about different axes of rotation. Okay, so with this simple example for system of masses, separate masses or separate bodies, we finished. And now let us go and have some practice to calculate moment of inertia of some distributed rigid bodies. So when they continuously change, distribute their mass, so means they have some density and shape. So in this case, when we have like moment of inertia, can be considered in the limit that we have very small part, very small mass of the rigid body, delta m, approaches to 0. And then sum over all these small masses of rigid body are I square times delta m. And this is nothing else as integral of r square dm. So it is convenient to operate not with small masses, but small volumes, because when we integrate, it's much more convenient to integrate over volume. So we can choose the appropriate system of coordinates for different shapes, and it will make our life easier. So in order to go from mass to volume, we need to operate with density. And in general, we can consider 3 cases: 1-dimensional, 2-dimensional when we have some plane, and 3-dimensional when we have literally like some volume. So in this case, for the linearly distributed mass, dm is equal to lambda dl, where lambda is linear mass density. So how many, for instance, kilograms per 1 meter of this rod. Another case, 2-dimensional, when we have some plane, dm, and be considered as sigma times ds. So sigma is surface mass density, and ds is very small area of this plane. So surface mass density will be like kilos per square meter. And the third case, dm, is rho dv. So rho is classical density, kilos per cubic meter, and dV is a very small part of the volume, elementary volume of the rigid body which we consider in 3 dimensions. Okay, so let us first consider some one-dimensional case. Actually, we don't need this y-axis, but it doesn't matter. So let's consider some rod with, so here we have our x-axis, and this is total length of the rod, which is L. Yeah, let's consider that this is 0x. This will be our y-axis. Then we will consider very small part of this rod at a distance x, and the length of this very small part of the rod will be dx. Now we want to consider the moment of inertia for this rod when it rotates about axis y. So we have this axis y, and we assume that our rod rotates about this axis. We want to calculate its moment of inertia. So we have linear mass density, lambda. That's why we can write that the mass of this small part of the rod, dx, is equal to the product lambda dx. dm is equal lambda dx. Now we need to use this equation for the moment of inertia of distributed rigid bodies and try to calculate it. So moment of inertia about axis y. So keep in mind, you always need to specify about which axis of rotation you calculate your moment of inertia, because as I mentioned before, it will be different for different axis of rotation. Will be integral r squared dm. It's like our general equation. And in our case, it will be integral from, so here will be minus L divided by 2. Here will be plus L divided by 2, like the coordinates of the edges of this rod. Then we will integrate from minus L divided by 2 to plus L divided by 2. And what do we have in our integral? It should be the distance times distance in square times delta m. So it will be x, because we have this delta x at distance x from the axis of rotation. Then we have lambda d x. Okay, so now we know that lambda is constant. Constant. We can take it out from the integral. Lambda minus L divided by 2 L divided by 2 will be x dx. Sorry, I made a mistake. I forgot to put here second power. So it should be like distance square, not just distance. And this will be lambda x cubed divided by 3 from minus L divided by 2 to L divided by 2. So what it will be lambda L cubed divided by 8 minus, then we have minus L cubed because we have negative L, minus L divided by 2. And that's why we sum them up. It will be lambda.
I think it's in denominator we have 24 instead of 8.
That you are partially right, because we just forgot this 3 here.
Ah, yeah, sorry.
Yeah, so this 3 we take factor out from this part. It's constant, so we use it with lambda, and then 2 in the third power will be 8. So good, thank you for comment. And then that means we have lambda divided by 3 L cube divided by 4, because we sum up 2 of this L cube divided by 8. And this is equal to lambda L cube divided by 12. Okay, let us rewrite it maybe on the, we have some space here actually. So we know that since lambda is constant, we can actually define it via mass, total mass of this rod, like capital M, and length. So it's actually a ratio of total mass to its length. And that's why moment of inertia about axis y can be written as m L cube divided by L, and here we have 12. We cancel out this L, and here 3 becomes 2. And finally, we get a capital M. Capital M times L squared divided by 12. Okay, so this is the final equation because it's kind of convenient to operate. It depends what is given, but it can be that like total mass is given and length, but we can always go from total mass and length to uniform linear density. So in both cases, these equations can be considered as final equations for this specific case. Okay, so with linearly distributed body, we kind of already figure out how to calculate this moment of inertia. Let us consider some three-dimensional case. So for this purpose, we can consider some cylinder. Let's say we have some axis Z, and along this axis Z, we have a cylinder. Okay, so now we need to define again this elementary mass, dn. In this case, since its cylinder is three-dimensional object, will be raw density, like three-dimensional density, times dV, some elementary volume. How we define this dV so it's convenient for us and it will not be painful process to integrate. So what we need to do, we consider smaller cylinder here with the radius r. So total radius here will be r capital of the cylinder, but we consider the internal inside the cylinder some smaller cylinder. And we consider another cylinder around this one. And the distance, the difference between radius of the internal and external cylinder will be dr, like some very small. So these two radiuses are very close to each other, which is radius r, and the second one is r plus dr. And also it goes down. So how we get this elementary volume? In order to get elementary volume via dr, so in terms of dr, we need to calculate the area of the internal cylinder, of the side walls of the internal cylinders is small, and then multiply this area to dr. This will give us the volume, elementary volume, which is in between these two cylinders, which we consider inside the big one. So it will be area of the side walls of this internal cylinder will be the length of the circle, which is 2 pi r, 2 pi r times length of the cylinder, which is L. So you understand what I'm doing. We have length of the circle, the base of the cylinder, and then we multiply this length of the base circle by L, and that's how we get the side walls area of the internal cylinder. And then if we multiply this also by dr, we kind of extend this internal cylinder from inside, make it larger. That will overlap some internal volume of the big cylinder, and this internal volume will be dV. This will be dV, some elementary volume inside the cylinder. And of course, we need also, so let's take it into parentheses and multiply it by density in order to get dm. So once we define elementary mass, we can apply our equation for the moment of inertia and calculate this moment of inertia. So moment of inertia of this cylinder Oh, now it's not about axis y, it's about axis z. It's this one, axis z, will be equal to integral r squared dm. So this is our equation which we derived earlier. Now it will be equal to integral r squared times our dm, and this will be rho L 2 pi r and dr. So instead of dm, we put this part, which we derived here. Now, what is constant? We assume that density is uniformly distributed all over the volume. Then we can take density, length, and 2 pi out from the integral. So it will be 2 pi rho L integral. And what we have in our integral is r squared, and here we have one r. Will be r cubed dr. Okay, now we need to integrate it for all cylinder. So we need to define the boundaries from where to where we integrate. And since we integrate along radius, so we integrate from 0, it's at this point where our axis of rotation is located, to r capital, which is the radius of our cylinder. This will be equal 2 pi rho L. It will be r in force power divided by 4 from 0 to r capital equal 2 pi rho L r force power divided by 4. Okay, so this we already did. So here we can cancel out these 2 and this 4. So eventually we get pi rho L r force power divided by 2. Okay, so this is done, but we also want to, so it's one option to answer this question when we define moment of inertia via the density rho. However, there may be another option, what we did before with the rod. We may want to have it via the mass of total mass of the cylinder. So in this case, total mass of the cylinder, let's define it m, and rho will be equal to capital M divided by volume. And this is capital M divided by area of the base times length of the cylinder. Will be pi r squared times L. So when we substitute this equation here for density, we can get the expression for the moment of inertia about axis of rotation z in terms of total mass, radius, and length. So without considering the density of the cylinder. So I guess now we will not do it. You can do it yourself. And we are running out of time now. We have actually some meeting on at 4. So there is also one topic, parallel axis theorem. It's approach how you can calculate moment of inertia for some rigid body about any axis of rotation which is shifted with respect to the center of mass. If you know the moment of inertia of this rigid body when it rotates about axis which goes through the center of mass. So I would recommend you to read about this parallel axis theorem by yourself. If you have some questions, we can discuss this, because we still have quite a lot of material to discuss on Friday. Somehow all this rotation around about fixed axis of rigid body was squeezed in 1 week, and it has quite a lot of new terms and concepts. So quite intense material for this week. So we will try to have discussion, finish our discussion of rotation of rigid body on Friday, but let's see how well it will go. Now for this discussion, you learn the new concept of moment of inertia, that it's analog to mass or translational motion. But if mass is constant, doesn't matter in which direction body moves. For the case of translational motion, moment of inertia is for the same body can be different if it rotates about different axis of rotation. So this is the main concept, and also you learn how to calculate moment of inertia for a system of bodies, of point bodies, and also for distributed bodies specifically in case of one-dimensional distribution and three-dimensional distribution. Okay, guys, thank you very much for attention, and hope to see you all on Friday. We need to try to finish our discussions on rotation of rigid bodies.
Thank you. Goodbye.
Yeah, you're welcome. Have a good evening. Bye-bye, guys.